The different procedures that we have available to design the layout of the facility. And the last thing we did on Monday was to explain or to go over the process of the systematic layout planning procedure, the SLP. And I want to go back to that. I'm going to review that one more time, and then I'm going to show you some examples that I posted today in the modules that I connected, or basically are examples of how to apply this SLP procedure to different scenarios. So again, the idea is to use the information that the tools that we have explained to collect information about the flow that occurs within the facility, and then use that as input for this process. So based on the input data and an understanding of the roles and relationship between activities, a material flow analysis or a front-to chart, like the one we developed in the lab last time, and an activity relationship analysis, the activity relationship chart, like the ones that we explained also in our previous class, are performed. So these are activities that we have to do in order to collect the information that we need for the application of the systematic layout planning procedure. So that's input. When we look at the activity relationships, there's an example here of an activity relationship chart. So you have all the departments listed on the left side of the figure. And then you have let's say, a classification scheme to define the type of flow or relationship that exists between two departments. So those are the closeness rating, which is here. These are not changing, as I explained last time. So these are standard. We have A for absolutely necessary, E for especially important, I for important, O for ordinary closeness, unimportant, and X, U unimportant, and X is when you definitely don't want those two departments to be together. And the reason those are based on the user or the decision maker, you can create a list and then put a code for each one of the reasons, and then use those codes to present a reason for the rating that you're providing for the relationship between departments. So for example, in this case, we have receiving and shipping. We define that relationship as absolutely necessary. So we want them together. And the reason in this case is because they have the same day. And so that's the activity relationship chart. And then for the flow of materials, which is here at the top left with the number 1, we create the flow front-to charts, like the one that we created in the lab last time. And using that information, that we can build what is known as a relationship diagram. So as I explained last time, we have those arcs that have that represent different, in that the type of line that you're using is representing the type of relationship that exists between these two departments. The departments are represented with the nodes. So here we have 9 departments from 1 to 9. Each one is representing a different department. And then we have different lines representing the different in terms of the strength of the relationship for both departments. So this is an example of how can you represent the relationship. So again, we go back to this closeness rating scheme, the definition of the rating scheme, and then we are using a line code to illustrate A, E, I, O, U, and X. So this is an example in which those ratings are represented with the lines. So again, we want these two to be close to each other. And then we have these two that we don't want them close to each other, and we can see that visually. You can see that with the coding that we have used for the lines. Another example of the relationship diagram. So we end up having organizing these departments now from 1 to 10 in this case, according to the strength of the relationship between them. So we want to make sure in this case that those that have multiple lines together, and for example, 5 and 10, they're located close to each other. And then those that have only one line, for example, 1 and 4, they're not necessarily have to be located close to each other. So this gives us a way to location of the departments. So we try to configure the layout based on the strength of the relationships. And then we can have the space relationship. So now we have the area that occupies each, in this case, each one of the departments. And this gives us a better understanding of how can we place these departments around the space that we have available. So the space relationship diagram is here. Involves the determination of the amount of space to be assigned to each activity. So again, we are using the area to represent the space that each area is going to occupy. And then using this information, we can try to come up with different designs or alternative block layouts for the facilities. So based on modifying considerations and practical limitations, a number of layout alternatives are developed and evaluated. The preferred alternative is then identified and recommended. Okay, so based on different configurations, so again, if you have a restricted area, you want to accommodate that those departments the best way possible, so that the communication between areas is there for those that have very high relationship score. But still you want to meet the space requirements. Okay, so that's the SLP or systematic layout planning procedure. So as I mentioned, I want to show you some examples. So the presentation or the slides that are in today's module are this deck of slides that I'm going to show now. So what I'm going to show you are 3 different examples of how to apply this systematic layout planning procedure. And these are the names. So the first one is more fictional. It's a very simple example just to get you started, and then we go to more application practical examples. So we start with the caveman layout, and then the novelty log spatial, which is a manufacturing department, and then the luxury manufacturing, which is a site planning application. So let's start with this one, the caveman layout. Again, this is an example just to get you to understand the process. Very simple. This overly simple case of making a layout by logical sequence for a caveman, says 25,000 years ago. So in this case, we want to play these 5 areas: fireplace, an area to sleep, an area for property storage, an entrance, and a work area. And we're going to use the ratings.
Excuse me, Professor.
Yes.
Your slides aren't showing anymore.
Oh, I'm sorry. Yeah. Thank you for letting me know. There you go. Okay, so we have these 5 areas, and we have a limited space that we need to use to accommodate these 5 areas. And we have the rating description. What else we have? We have this square matrix or area that we are going to use to represent the length. You see 1 feet, 1 foot here. So we are using the rating description, and we are preparing this chart in which we're gonna define the relationship between the areas. So again, we have 5 areas. And using the rating description, we are gonna allocate some scores here. So between fireplace and sleep, we have an O. Between fireplace and property storage, we have a U. Sleep and property storage, we have I, which is important. Entrance and, for example, sleep, we don't want those to be close to each other. So the entrance have to be far from the sleep area. So that's why we have an X and so on. So we built this relationship chart to illustrate the type of strength of or flow of information. In this case, there's no flow of information, but the strength of the relationship between these 2 areas. So if we want them to be close to each other, then we assign a high score. If we don't want them to be close to each other, then we can go down through the list in terms of defining the relationships. We also have some additional information here in terms of the area space and the shape that is desired for each one of the areas. And we have the reasons. So 1 is warm, 2 is ventilation, 3 is protection, 4 is convenience, and 5 is light. So if you see in addition to the rating description, we have the numbers below. So for example, sleep and property storage, we have an I, which is important. And the reason is because of protection. Okay, so we want to have those 2 close to each other because of that. So we have the activity. And now from here, we can start building the connections. So now we're going to use four lines to represent an A, 3 lines to represent an E, 2 lines to represent the relationship I, and so on. You see between 1 and 4, we know if you look at the chart, between 1 and 4, we have an E, right? So that is represented with 3 lines. And then we keep adding to our diagram number 2, we're adding 5, and then 2 and 3. And then until we get to diagram 3, that is illustrate that these 2 must be close to each other. 4 and 3 must be separated, and 4 and 2, they must be separated as much as possible. 1 and 5 should be next to each other, 4 and 5 too. And 1 and 4, there's no, it's really not necessary, but if you put them together, there's no problem with that. So we arrange this based on this description. So we can play with the movement of these areas using the diagram. And then what we want to do is say, okay, now I have this configuration. If I try to put that configuration inside the cave, would that fit? So remember that we have some area information here. We have also the required shape. So using that, we can generate a possible layout that is going to meet these requirements. For example, yes. So for example, 1 and 4, they're next to each other. That's satisfied. 4 and 5 are next to each other. 1 and 5 are also next to each other. So those 3 requirements are satisfied. 2 and 3, they're next to each other. And we want to make sure that 3 is not close to 4. So 3 is not close to 4. And 2 is not close to 4. So again, 2 is very far from 4. There's no wall being shared. And that completes the exercise. Okay, so we go from defining the relationship, from to chart, activity chart, and then based on that, we create the assignment of the arcs based on the rate description. We build the chart or this figure diagram, and then using that information, we try to accommodate those departments areas in the space that is available. And that's the SLP procedure. Questions about this example? Okay, so let's look at one example that is more practical. So here's the final drawing. This is a manufacturing process. So we have novelty, luggage, special. And this is a company that produces to order an infinite number of end products. Each item is ordered special. However, all items involve printing on thin plastic sheet material. End products are tennis racket covers, beach bags, windbreaker, jackets, and so on. Most of the product have printed on them special logos, press, commercial messages, graphics, or small talk statements. Printing on the material, while it's still flat, is the key service provided. Sport clubs and high schools are typical end users. The overall layout of the plan is shown on the sketch. So this is the overall layout for the company. So we have all these departments. You see there's some space here for lunch, office space, and so on. In this example, we're going to be focusing on one of these departments. Let's continue. Which is the sales screen department. This is the department that we are gonna study. It's continually jammed. Although there are only 3 workers involved, there is excessive congestion and plant spoilage. The 3 workers have convinced the plant manager that if they could open an exit door to the area immediately west of the department, the flow of the material will be improved and the congestion reduced. That is convincing. It's a convincing argument, and the plant manager has said, okay. Okay, so the idea is, can we build another door for this department so we can improve the flow? Before opening a new door and just changing things around, he was asked the 3 employees, one of whom is a departmental leader, to show him a plan of a proposed layout for their area with a new door opening in the west wall. Okay, so we are gonna create a wall here, and we need to change the design of the department or the layout. So the problem is, assume that you are the team leader for this detailed layout planning project. Follow the SLP methodology to make at least one layout for the area. Assume that existing door on the east-west aisleway will stay. So this is gonna stay, this door right here. And a new door will be open at the west end of your area. The area is currently walled off from the rest of the plant, even though doors are open most of the working hours in order to reduce dust and properly ventilate the area. Okay, so here's the information that we have about the department. We have an activity area number, description, and we have the equipment name and dimension. So we have the entrance from cutting, which is the existing doorway, and we have an exit to assembly, which is proposed doorway. Right, so we are proposing this door to assembly. And you see, there's no wall in this part of the department. Right, so that's more like an open area. We have the incoming hold, which is a space for 6 2x3 carts. We have the finished hold, which is a space with 3 2x3 carts. We have an auto paint press, that's a machine, dimensions 4x6. We have a hand paint press, which has dimensions 3.5 feet by 4. And we have this dryer, which is pretty long, 44 feet by 4. We have storage area, we have a cleaning tank and table, we have this screen preparation table, and we have this desk with the time clock. So we are going to look at these spaces, and we try to arrange them within this departmental space in the best way possible using the SLP procedure. So again, we go back to the activity chart, and we are listing every area, including the entrance and the exit doors. So those areas, again, were listed here. So we have the entrance, the exit, the incoming hall, finish hall, all 13 of them. And now we're going to look at the type of relationship that we need to have between those areas. So for example, those areas that need to be close to the entrance will be, will have a high absolutely necessary score with an A. And those that are not necessarily related to the entrance will have a different score, like U, unimportant. So you can see here that for the incoming hall, the entrance is especially important, so we have an E. For the auto paint press is important. For the hand paint press is also important, but for the rest of the areas is not important at all. So we know that those three areas needs to be close to the entrance. And the exercise continues. So the challenging part is to collect this information, right? You have to talk to the people that are involved in the process. They will give you the feedback, and then you put together this chart using that information. We have the reasoning behind the, the reasons between the, for the codes. So we have 5 reasons here, and those are the ones that are listed under the letters. So once we have this information, what's next? What do we do next? Do you remember what's next? You're gonna come up with this network, right? A graph that is going to use this information and is going to depict the arcs in the network. So we also have some additional information about the dimensions. Those were shown on the first slide of the example. So here's where you have additional information about the equipment, dimensions, height, area, machinery, operations work, and maintenance area, and so on. So here's the area that we are going to use to design our new layout. This area now has an exit door, a new exit door to assembly right here that was non-existent. And then we also have some space here that is fixed. This is called existing paint storage area. So as I mentioned, we can build this activity relationship diagram based on the scores. So now we can see with the diagram which departments needs to be close to each other. So in this case, 4 and 8, 5 and 7, they have to be close to each other. And then we have more flexibility with 2, 1, and 3 and 6. We keep adding to our design until we finalize we add all the departments. In this case, we have 13. So all of them are represented here. So you can see now that as you increase the size, right, of the areas and departments, the diagram will get kind of messy, right? So it's important to make sure that you keep track of the type of arcs that you are using and that those are represented clearly. And now you can start arranging this based on those relationships. And also in our case, since we know how this area looks like, we can consider that shape of the department as part of our organization scheme for the diagram. So we are looking at the exit doors, entrance here. We know that 2 and 1 are representing those areas. So we need to make sure that those are close to those doors. And then we can try to arrange the area or the network based on the area. So this is what we end up with. Okay, 8 and 7 Here, once we get the final drawing, we can put the information with the areas, and then we can see whether or not there's a feed corresponding to the drawing or the figure and the area that is available. In this case, it fits nicely. So we have the dryer in the middle, and then we have the rest of the areas against the wall, and the doors are in the corresponding location. And this is the final layout of the area. Okay, so we get the idea, again, is that you are relocating, in this case, the position of this equipment and these areas, storage area and so on, based on the type of relationship that exists between these areas in the department. So this is the final layout for that one. Okay, we have one example. The one that we just discussed was focusing on the redesign of an existing department. Now we're going to look at an example that is going to look at the entire facility and is going to allocate the departments inside the facility. And that's called the Luxury Manufacturing Ltd. So here's the area. This is a luxury manufacturing, develops, produces and distributes toiletry and personal care products. The company is located in Bangkok, Thailand, and is subsidiary of an international firm. The company has enjoyed sustained growth, and its top management foresees the end of 4 additional facilities. After a thorough investigation, a new site was selected in Saraguri province, 85 kilometers from Bangkok. The site is shown below. So this is the area, the site for the new factory. We have 220 meters by 170 meters, and we have a highway going in this direction, highway going in this direction, and there's another type of street going in this direction where no trucks are allowed. And there's a dedicated back dirt road here. So highways are here, no trucks are allowed in this area. Top management wants a master site plan so that the available space can be effectively utilized for the long run. That is, the initial need for building is only about 1/4 of the amount of the site available land. Okay, so the initial need for buildings is only 1/4 of the amount of the site available land. The company has room for doubling its under roof space and has open land for roads, parking, water, retention, and utilities. It wants a site plan now, good for this future expansion. The initial space needs call for separation of product facilities from warehouse and supporting services. Also, laboratories must be segregated in their own building. Note the restriction for commercial vehicles on the west side of the property. North and east highways are not limited for commercial vehicles. The site slopes gradually to the southeast. So, the problem, you have been assigned to develop a master site plan for this new site when it will grow to full site company. So how would you proceed? You're gonna proceed using the SLP procedure. So we start with the activity relationship diagrams. So based on, again, you have to go talk to the people about the areas that are needed, right? The lab, the office, the production warehouse, and the type of connection and flow that is needed between those. And we're going to use the activity charts to do that using the ratings that we have studied so far. So this is an example of the final assignment of these ratings for between these areas. And we're going to use this information to build our network, our diagram with the nodes and the arcs. So we have some additional information here about the area of each one of these departments. So the square area is here, and we have listed the area for those. So we can use that information to design the final layout. So we have a couple of diagrams here, diagram 1 and diagram 2. One of them goes up to 8. Then the second one includes 9 and 10. But they're similar. Again, we follow the ratings. We assign the number of lines according to the ratings, and then we draw the network. As you can see, 2, 7, and 6 are very have many lines, so the relationship is pretty high. So we're going to need to make sure that those are close to each other. 4 and 5, same thing. 6 and 8, they are especially important. So we can build our initial arrangement based on that. So this is one of the final diagrams using, again, the relationship between these three is very high, so we have to make sure that they're close to each other. These two as well, and these two as well. So coming up with a final design, you can see how this network looks like and how is that related to the final areas in the space that is available. So again, 6 and 7 is closed, 7 and 2 are also closed. We have 8 and 6 close to each other. There's no relationship between 7 and 10, so that's not shown here. 4 and 5 are close to each other, and then those are also connected to 6 and 7. So another example, you get the idea. Start with the process of collecting the data, assigning the ratings for the flow, build your network, your arcs, your nodes, rearrange those based on the areas and try to fit the area that is available for your layout. And then you can present, this is just one option. There might be other options, but they have to correspond to the area that is available, and they need to make sure that they're close, that you're showing closer between those areas that have very high score between them. So when you build this for the homework, for the assignment, not expecting you to have the same design, right? I'm expecting to see a design that is meeting the requirements in terms of closeness based on the ratings. So you can have one design that is correct, another classmate can have a different design, but they still meet the closeness of the ratings. It is also correct. So it's not like there's a unique solution for the final arrangement. Is that clear? Okay, so, and then the solutions that you're going to see for this problem, again, it's just one solution that meets the requirements that are provided for the problem. Questions? Yes. For this particular process, for the SLP process, there's a lot of manual processing that needs to be done. And at least in my experience, there's no software that will do this automatically. For the other type of algorithms that we are going to discuss, for example, Craft, there are software that you can use that you can just input the information and it will give you the solution based on the algorithm. But for this one in particular, I'm not aware of any software that will do this automatically because it involves a lot of judgment, right? So that's why I haven't seen, at least for this particular process, in a computer-based program that does it. Good question. Any other question? So for the Craft, I will share with you some of the code that is available. I think there's an Excel add-in that can be used, but we haven't got to that point yet. Good. So here's the final layout, including those areas: stormwater retention, parking, car and bike space, parking space. And that's the final slide. Then we can go back to this one. So that's for the SLP. But as I mentioned, there are other algorithms or processes that we can also use to solve the same type of problem. This is just one method, very popular method because it requires a lot of feedback from many people. So it's not just one person trying to come up with the design, but it requires the input of also the people that are involved with the operations. And it's very practical in the sense of people can understand what's going on. So you can present them, this is how we got through the process, and this is our final design. So let's talk about the algorithms approaches. The layout procedures presented in the previous section provide a framework to construct or improve a layout, but they do not provide a formal procedure or algorithm for some of the critical steps associated with the layout design and evaluation. So for example, when you look at the process that we just discussed, there's a lot of manual information and computation that is done, movement, drawings happening, but there's no like a formula that is telling you if you do this, you're going to improve your performance by X amount, right? That you don't see that. The type of algorithm that we're going to discuss now, they are steps that are going to use some type of performance measure to tell you, okay, if you move this area to this location, you're going to improve your design or your performance measure by this amount. So the models and algorithms we present in this section provide us with objective criteria to facilitate the evaluation of various layout alternatives that emerge in the process. Most layout algorithms can be classified according to the type of input data they requires. So we talk about this different type of data: qualitative flow data, such as a relationship chart; quantitative flow data, such as a flow matrix expressed as a front-to chart. And some algorithms accept both relationship chart and front-to chart. Okay, so it could be qualitative, focus on qualitative data, it could be focus on quantitative flow data, or it could be using both type of information, relationship chart or front-to chart. Layout algorithms can also be classified according to their objective function. So, for example, if you're familiar with linear programming, operation research, maybe those of you who are in industrial engineering, if you took IE 3340, algorithms based on an objective function that is trying to minimize, meaning that it's looking for the solution that is going to get you the minimum value, or maximize, it's going to be looking for an objective function that is going to give you the maximum value. So algorithms can be classified based on those two objectives too. So if you're minimizing, you're trying to minimize the sum of flows times distances. So again, there's a lot of movement, as you saw in the previous lecture. We can quantify the amount of movement that is happening between the areas. If you account also for the distances, we can design algorithms that will try to minimize the combination of the two. So the flow times the distance, that's the total travel that occurs within the facility. And then the algorithm can tell you, if you put these areas in this order, you are going to minimize the total travel distance inside your facility based on these flows that you have. Or maximizing the adjacency score. This is looking at, okay, you have these scores for the relationship that occurs between these areas. Let me use that information and let me find you the location of the departments that will optimize or maximize those scores. So if you place these two together, that score is going to be higher. If you place them separate, the score is going to be lower. And then the formulation that you see here, these are the mathematical formulations based on operation research. We have the objective function, this mathematical equation for the distance-based oriented is the summation for the flow times the cost times the distance from department I to department J. So again, the flow, how much it costs you to move that from each department to another department. So are you using a person? Are you using a forklift? Are you using a conveyor? Those have different costs. So you take into account the cost of movement and also the distance, how far you need to move this. So the combination of the three will give you a performance measurement of the flow. And then the summations are going to be looking at each possible combination between departments. So if you have 100 departments, it's going to look at every possible combination between the 100 departments. So this could be a very long function. Yes, so that's the objective function. The other one is looking at the adjacency-based objective. It's just looking at the flow. So how high or how low is this flow? And if the Xij is the adjacent of department I and J in the layout, meaning that if they're together, then you assign a binary. We can assume that this is a binary variable of 1, they're together. So that is going to increase your score. If they're not together, it's going to be a 0, so that's not going to have an impact in your objective function. M is the number of departments. So two different ways of evaluating the same information. Layout algorithms can be classified according to the objective function. So an algorithm can be focusing on minimizing the sum of the flow times, distances. Another algorithm can be looking at only the adjacency score and maximizing those. And using both algorithms, you can get different designs. So it will depend on how, what you value most in terms of making the final decision. And here's a list of algorithm approaches. I'm putting in red the ones that we are going to cover in class, but there's a Pairwise and change method, graph-based method, graph, MCRAS, block plan, MIP, logic, and multiple. So let's start with a pairwise exchange method, and then in our next lecture, we're going to look at, we're going to start with the graph-based method, and then in our next lecture, we're going to talk about the graph method, which is the one that I was mentioning. Okay, so let's talk about this one. The graph-based method looks similar to the one that the SLP procedure that we just discussed, but now we're going to have a quantifiable method, or we're going to have a quantifiable function that is going to tell us, it's going to direct us on how to proceed in terms of moving departments in the facility. So the graph-based method is a construction type algorithm. Okay, so this is used if you don't have an existing layout. So construction is basically using under the assumption that you're building this from scratch, this facility from scratch. And this uses the adjacency-based objective. So this type of maximizing the adjacency scores. The adjacency score does not account for distance, nor does it account for relationships other than those between adjacent departments. Dimensional specifications of department are not considered. The length of common boundaries between adjacent departments are also not considered. The arcs do not intersect. This property of graph is called planary. So we are not going to allow these arcs to intersect each other. And the score is very sensitive to the assignment of numerical weights in the relationship chart. So let's build, going to use this as an example, and we're going to work through this example to explain the strategy. So we're going to start with consider a company that wants to develop a layout for his new 5 departments of equal size. So we have the relationship chart here. And we can also develop a relationship diagram. So this is going to be like a network. Okay, so let me draw the network here. We have 1, 3, 2, 4, 5. And then the flow between 1 and 2 is 9. The flow between 2 and 5 is 7. The flow between 2 and 4, 13. 4 and 5, 2. 3 and 4, 1. Got the 9 already, 1 and 2. 2 and 3, this one is 12. And then we have 1 and 4, it's 10. And the rest are zeros, so there's a 0 here. And there's a 0. And so those arcs are not representing anything. I mean, just putting them there to complete the process. But there's a 0 below, so it's like not having an arc. So this is the relationship diagram. It's basically illustrating the same information that is in the relationship chart using the arcs and the nodes representing the space. So we're gonna do step 1 on the next slide. Can I move to the next slide or just wait? So in step 1, from the relationship chart, select a department pair with the largest weight. Okay, so we're going to look at this relationship chart. And then we're going to see that the largest score here is 20. So department 3 and 4 are selected to enter the graph. Okay, so we're going to start building this step by step. So we're going to start with department 3 and 4. Because they have the highest or the largest weight. Okay, remember we're going to guide our decisions based on these numbers. So this first step is quite simple. We select the 2 that have the highest score. And we start building this graph. Then step 2, you're going to select the third department to enter. The third department is selected based on the sum of the weights with respect to departments 3 and 4, which are the ones that we already selected. Okay, so now I'm going to look at the rest of the departments, and I'm going to see in relation with those that I already selected, which one has or which department has the highest score. So how do we do that? We're going to have the rest of the departments that haven't been selected. Those are 1, 2, and 5. And the departments that are already selected are 3 and 4. And we have total weight here. So what is the score between 1 and 3? Between 1 and 3, the score is 8. And between 1 and 4, score is 10. So the total is 80. Then I'm going to look at 2. Score between 2 and 3 is 12. The score between 2 and 4 is 13. So total is 25. Then the last one, 5 and 3, 0. 5 and 4, 2. So this is a 2. So score is 2. Okay, so now we have the totals for all possible combinations. So the one with the highest score is 2. So that means that 2 is going to enter the graph. Okay, so we are guiding our decisions based on the highest score. So I got 3 and 4. Now I'm going to add 2. So the new graph so this one is the best. So new graph, we have 2, 3, and 4. So these three are close to each other, 12, 13, and 20. And now 2 will be part of the graph. The only 2 departments that haven't been assigned yet are 1 and 5. Okay, so let's do the next one. Can I move to the next slide? Okay. So do the same process. Now we have 1 and 5. And the departments that are already in the graph are 2, 3, and 4. We have the total. Okay. So between 1 and 2, this is a 9. 1 and 3, got an 8. And 1 and 4, we have a 10. This is 27. Between 5 and 2, we have 7. 5 and 3, we have 0. And 5 and 4, we have 2. It's 9. So this one is the best. So 1 is going to enter. So our current graph, we have 2, 3, and 4. We have 12, 13, 20. And now we need to place 1. So up to this point, we've been able to locate this in this triangle. From now on, we're going to be looking at the different phases of the figures that we are creating. So this one that we're going to add now is simple because we can just place that in the middle. It is going to be connected to 3, 4, and 2 without problems. But then you'll see what's going to happen on the next one. So this is 9, 10, and 8. Okay. So we still have 5. We know that's the only one missing. So the question is, where are we going to place 5? Remember that the algorithm, if you look at the notes here, here. So we cannot cross the arcs. Okay, so we need to decide where are we going to place this department. Are we going to place it are we going to put it here in this, inside this triangle? We're going to put it inside this triangle. Or inside this triangle. Okay. So that's what we are going to try to address next. Determine on which phase to insert the last department. So go back to the table. So we have 5. 1, 2, 3, and 4. And 5 and 1, we have 0. 5 and 2, we have a 7. 5 and 3, we have a 0. And 5 and 4, we have a 2. Okay, so what are the phases here? Go back to this figure. We have 1, 2, 3. That'll be this, and this. So that's one of the phases. 1, 2 phases. And the total. So we have 1, 2, 3. That's this triangle, the yellow triangle is 1, 2, 3. We have 1, 2, 4. 1, 2, 4 is that green triangle. We have 1, 3, 4. One, 3, 4 is that blue triangle. And then we also have the outside. So the outside is also considered an option or a phase. Right, so the outside will be given by 2, I'm sorry. 2, 3, and 4. So those are the possible options. We can put that node outside on the orange area and then connect to the nodes. We can put it inside. If you put it outside, you're basically saying that the node has no connection to 1. Basically, that's what this is saying, because you cannot cross the arcs. You can have 2, 3, and 1, which means that you're basically separating that node from 4. You can put it in 3, 1, 4. You're separating that from 2. So you see what's happening, right? Like in the phase that you decide to place this new node, you are separating that from one of the other nodes in the layout. So let's look at the totals for each one of these phases. So we're going to be looking at these numbers. 1, 2, and 3 So we look at 1 is 0, 2 is 7, and 3 is 0, so the total is 7. We look at 1, 2, 4. 1 is 0, 2 is 4, 2 is 7, I'm sorry, and 4 is 2. So this is 9. 1, 3, 4, 0, 0, and 2. So this is 2. And 2, 3, 4 is 7 plus 2 is 9. So we have a tie. We have the best here and best here. So we have two options. We can put the new node in this green, right? Is 1, 2, 4. Or we can put it outside. 2, 3, 4. Which if you put it outside, it makes sense, right? Because 0 is assigned to 1. So you don't need to connect that node to 1. And then 3, if you put it in this phase right here, the score for 3 is 0. So you don't have to interact with 3. Okay, so that's why these are the best options. You put it here, there's no interaction with 3, so you don't need an arc connected to 3. You put it outside, you cannot connect it to 1, but that doesn't matter because your flow between that node 5 and 1 is 0. 0 and 0. So let's build that. One of the possibilities. So we're gonna put 5 here. Gonna put 5 there. That's one of the options. So the graph is gonna look like this. Number 2, number 3, have 4, we have 1, and we have 5. These 2, then we have these 2. This is 12, 9, 7, 13, 8, 20, 10, and 2. Okay. Yes. These numbers, 7, 9. Yes. So you this 1, 2, 3. These spaces. Yes, those are based on these areas that have marks, right? So those are areas that are inside this figure. So you see this yellow area. You can name that 1, 1, 2, 3. So that's the first one. And then we have 1, 2, 4. That's another one. And then I have 1, 3, 4, which is the third one. And then the area outside that takes 2, 3, and 4. Okay, so those are the possible. Remember that we cannot cross yards in this strategy. So we are looking for adding a new node, and we are looking at the possible areas in which we can place that node. So we can put it in the middle here, in the middle here, in the middle here, or outside. Okay.
My question was, well, how did you get the value?
Oh, the value. This. So now that you know the last requirement that needs to be added is 5. So we got this based on the activity chart. So from 5 to 1 is 0, 5 to 2 is 7, 5 to 3 is 0, and 5 to 4 is 2. So we have this course, and now we look at each phase. 1, 2, 3. Look at 1 is 0, 2 is 7, and 3 is 0. So the total is 7. Okay, and then continue. Good question. And then after completing this process, now we have a network that tells us, this is how you should organize your departments if you want to maximize the adjacency scores. And we can use this figure to accommodate the area or to accommodate the location of our departments in a specified area, which is what we're going to do next. We can construct a corresponding block layout. We are given the space area based on that network. Okay, so if you look at this network and this one, they're the same. Now we have included the space areas. We have one in the middle, 5 next to 1, and there's a little hallway here that is connecting 4 and 2. Has on purpose because we need to make sure that 4 and 2 are connected. So that's what this is doing. And rearrange, once we have the areas, we can rearrange the space based on the location of the nodes and the arcs in our network. So again, this one goes a step further when we compare it to the SLP process. Now we are, instead of just basing our location of the departments just on how things look on the graph, we are adding these scores that are guiding us in terms of who should be added next. And then we come up with the same type of network at the end, but this network is based on those scores. It's not just based on visual representation, but we have those scores that are guiding our process. And this is the final layout. And that's the last slide for today's lecture. So I'm going to stop here. Any questions? So your new assignment, you'll see that there are questions associated with this. There's questions associated with the SLP process. Yes, sir.
So is it a block diagram?
Yes. A block diagram would be something like this. Yes, yes. Good question.
And what's the triangle one just above it? What's that one?
This is just a network.
Like the one at the very
Oh, the activity chart.
activity.
Yes, yes. Good question. Yes. Any other question? Now, then I'll see you next week. Have a good weekend. Yes, sir. Yes. Any other question? Okay, so have a good weekend. See you
Thanks,
on Monday.
Professor. Have a good one.
Yeah. All right.
Exam is the 21st, right?
21st, yes.
Yeah.